Today, we're going to tell you about a surprising class of vulnerabilities in differential privacy software and how we fixed it. So as you might know already, the gold standard approach to publishing or sharing sensitive data is called differential privacy. The key idea is quite simple. You add statistical noise to your statistics so that the impact of one person cannot be detected. So let's see how it works in practice. Say you want to answer a simple question. How many records are in a database? With differential privacy, you want this answer to not depend on a single person. So if you have 100 or 101 records, you shouldn't be able to detect the difference. You can provably prevent detection using the Laplace mechanism as an example. Say that the true answer is 100. Instead of returning exactly that answer, you would pick a random number from the red distribution here. If the true number is 101, you're going to sample a number from the purple distribution. Note that the shape of these distributions. In that case, one is always exactly, or at most, twice as high as the other. So every answer you get from one scenario, you could get from the other scenario with a similar probability. Here, it's a similar probability up to a factor of 2. Now, let's put our evil mask on, because that's why we're here, and notice something interesting about these lines. The interesting thing is that they're lines. As in, the mechanism, if you look at the papers, is defined with continuous math. To implement it perfectly, it means that you would be supposed to return a number with infinite precision. But computers don't have infinite precision, right? So what happens if we implement this noise addition step naively, and we zoom in on some of these curves? If we implement that naively, and we visualize the distribution of floating point numbers that we get from these two lines, we get something that doesn't really look like lines anymore. Here, the red ticks represent floating point numbers, and the arrows represent which floating point values can actually be reached by each distribution. And we're in for a bad surprise here. The distribution do not reach all of the possible values. That's very bad news, because every value, some of the values can only be reached by one distribution, not the other. I've circled a couple of them here. So if here, in that example, if you return the value 3.75, the first circle here, then we can be sure that the true answer was 101, because the red line could not have arrived there. That's bad, because that's exactly what differential privacy was supposed to avoid. So that's a vulnerability. That's something that doesn't work as we expect, and that sort of opens up a privacy vulnerability. So why does this happen? To understand more what's going on here, let's take a look at a naive implementation of the Laplace mechanism. First, we're going to generate two random things. The sign will decide whether we're going to add positive or negative noise. And a second number is going to be just a uniform number between 0 and 1. Second, we're going to massive these two things into some math to get the noise value. Here's the third line. And we're going to return the sum between the true value and the noise value. 10 years ago, differential privacy researchers named Ilya Mironov noticed something interesting. When you ask a standard library, like in Python, Java, C++, Go, whatever, to give you a uniform number between 0 and 1, it actually will not give you all of the possible values between 0 and 1. Typically, it will just generate 52 bits. So that's a very big number divided by 2 to the power of 52, and that's what you're going to get. So the very small values that are very close to 0 and have lots of precision, you're never going to get. When you pass that value into the math formula, you end up with these holes that we saw earlier. These are floating point values for the noise that just cannot be reached. Yeah, I see people facepalm. That's exactly the right reaction here. This propagates to the sum, leading to holes in the output, leading to what we just saw. As I said, this was discovered in 2012 by Ilya Mironov back then. That was more than 10 years ago. So when we started building floating point primitives into our platform at Tumult Labs, we assumed that the problem would be basically solved, that you could just take an off-the-shelf solution and run with it. Curiously, we found that the problem actually had subtle trade-offs, and that everybody was doing different things. We found two attempts that were actually kind of interesting. One approach says, well, the noise is the problem. The holes in the noise are the problem. So we can change the way we generate the noise to avoid these holes. Another approach is to say, OK, maybe avoiding these holes is complicated when you do floating point math. So instead, we're going to combine multiple noise samples to maximize the randomness and make it harder to sort of reverse engineer where the holes are. But interestingly, among these two approaches from two different platforms, none of them came with a proof that they were secure. So that seems like a good opportunity to put our evil mask back on and think about our original implementation again. Even if the noise generation is perfect, what happens when you add it to the true value at the end? Taking another look at our floating point line, here I'm showing both sides of 0. And I've annotated each of these intervals, each interval between powers of 2 with their precision. There are as many floating point numbers between 1 and 2 as there are between 2 and 4, and so on. This means that the smaller the floating point number, the shorter the intervals around it get. For example, between 1 and 2, all of these numbers are multiples of 2 to the minus 52. Let's add noise to the number 1.25, which has precision 2 to the power of 52. We're going to see where the sum can end up, depending on how large the noise is. Okay? Bear with me, there's two options. First option, the noise is small. Here, it's between minus 0.5 and 0.5, so less than 0.5 in absolute value. In that case, because the noise is small, when we add it to our original value, it can't move too much, right? It's going to stay kind of around our original value. The purple brace here represents that. This means that in that case, we're going to go down at most one level in precision. The precision of the output is going to be 2 to the minus 53 or above. So even if the original noise had a very, very small precision, the sum is always going to be rounded to a multiple of 2 to the minus 53. OK, that was option 1. Now what about option 2? If the noise is large, it means it's like above than 0.5 here in absolute value. And if we look at our line here, it means that its precision, the precision of the noise, is also 2 to the power of minus 53 or above, right? So we're adding two numbers that are both multiples of 2 to the minus 53. So the sum is also going to be a multiple of 2 to the minus 53. So in both cases here, we can generalize the argument to say that when you add a number that in an interval with a certain precision, you're always going to get a multiple of the precision right before that. OK? So that's a very interesting fact, because if we take all of the possible outputs of the sum after adding noise to 1.25, and we compare them to adding noise, for example, to 0, which is not going to have any of this precision issue, well, if the sum has a precision that's too small, we know it must have come from the bottom distribution. That's where the true value was 0. Otherwise, we could not have reached such a small precision when summing the value with the original value. So it's very frustrating, because 10 years after the original vulnerability, we're just back where we started. We can guess which number we've picked based on just the output, which, again, was exactly what we were trying to avoid in the first place. So how do we fix this? I'm going to give it over to Sam, which will explain what's the right way of, or what's a possible way of fixing these problems.
Thanks, Damien. Right, so how do we fix this problematic code then? So we know the sum itself is sensitive, so we need to fix the entire routine at once. Generating secure noise isn't enough. So the general idea is to directly generate the distribution we want, centered at the true value, instead of generating noise and adding it to the sum. So here you can see the cumulative distribution function for the Laplace distribution centered at 100. Second, we want to use inverse transform sampling to generate a sample. So we pick a number between 0 and 1, use the inverse of the cumulative distribution function to transform the sample into a sample from the distribution, and finally round this sample to the nearest float so that it's something that a computer can represent, and we return this. Of course, we can't do this because of floating point issues, so instead we're going to try to simulate this process. All right, so instead of sampling a value from the y-axis, we're going to sample an interval. So here in the first step, we've cut our original interval from 0 to 1 in half, and we choose one of these halves. Then we transform this interval using the inverse CDF, and we get an interval on the x-axis. So we call this interval refining. at each step, we're going to sample 1 bit, cut our interval in 2, and then do this transformation. One way to think about this is that we've sampled this real number that we talked about before uniformly at random from 0 and 1. And at each step, we get to look at an additional bit from the real number. And this gives us a new interval where we know this real number must live. So here's a further refinement and another one. You get the idea. We can use arbitrary precision floating point arbitrary precision floating point values to represent the ends of this interval. So we can make the interval as small as we want and make it as precise as we want. So then the question is, when do we stop doing this? OK, so first let's zoom in a bit. Here, we've done a bunch of iterations, so the curve looks like a straight line at this point. And you can see successive floating point values on the x-axis. So next, we look at our intervals, and we look at where the ends of the interval on the x-axis would round to if we rounded them to the nearest floating point value. So here, the ends round to 2 different floating point values. So if we think about our hypothetical real number, we don't know where it is in this interval, so we don't know which floating point value this real number would round to if we knew where it was. However, once the interval is small enough that both ends round to the same value, we can terminate and return this value. Again, going back to this hypothetical real number, regardless of where it is in the interval, we know that this real number would round to this float, so we don't need a tighter bound on what the number is. So therefore, this process simulates sampling a real number and rounding to the nearest float. Yeah. All right, there's one more detail, and that's that we can't compute the inverse CDF exactly. Right? So these dotted lines can't be computed exactly. This is because the inverse CDF has, for example, a logarithm in it, so this can't be computed exactly. Instead, we can compute an interval containing the true value. So for each endpoint of the interval on the y-axis, we can compute an interval corresponding to that endpoint on the x-axis. And then to construct the final interval on the x-axis, we can use the left endpoint of the left interval and the right endpoint of the right interval. So this makes our final interval on the x-axis slightly bigger, but everything else works the same. All right, we think this is neat for a couple reasons. The first is that as we saw using the hypothetical real number, our algorithm is equivalent to sampling a real number and then rounding to the nearest float. So this gives us an easy proof that it satisfies the desired privacy guarantee. Secondly, I showed this using the Laplace distribution, but we can replace it with other noise mechanisms, and it would work just the same. And third, it converges fast in theory and practice. One optimization we can make in practice is to sample multiple bits, say 50 bits, instead of 1 bit in each iteration. When we do this, the algorithm almost always terminates in 1 or 2 iterations. All right, so there are a couple things that I hope you take away from this talk. First, differential privacy can have vulnerabilities. And when we find one of these, And when we find one of these vulnerabilities, we shouldn't think about how do we make this specific vulnerability go away and go for an ad hoc solution. Instead, we should have proofs that the implementation matches the theory. Right. The good news is that often we can find principled approaches that remove these vulnerabilities entirely while still maintaining the design goals that we want, like simplicity and efficiency. And finally, what do you need to do to prevent these? Well, nothing, just use a library that has a proven fix. So speaking of which, here's a summary of our findings from the state of open source tools today. So 2 libraries are still vulnerable, one of which is no longer being worked on. OpenDP was initially vulnerable, but is fixed using discrete versions of the distributions. This is similar to Google's approach, and this also comes at a small cost in the privacy guarantee. As we note here, our approach doesn't require any discretization parameter, and it can be applied to a larger variety of distributions. And as a final note, none of this is possible with proprietary code, so thank you for shipping open source code. Thank you, and yeah, please ask questions.